Okay, good evening everyone. In a few minutes, we are about to begin for surface modeling using Onshape and FeatureScript. So once more, in a few minutes, about to begin surface modeling using Onshape and FeatureScript. So if you think once more, this live stream is beneficial to someone you know, please invite them to join us. Okay, so see you once more in a few minutes. Okay, so once more in a few minutes, about to begin surface modeling in Onshape with the feature script. And before we begin, of course, not only in our community, we would like you to be technically competent and proficient. We want you to level up also with regards to your leadership skills. So, in addition, inviting you tomorrow night. It's unleash the leader in you, expanding your mindset to achieve a greatness. So that is for tomorrow at the 7 p.m. Okay, level up with leadership. Also inviting you to join us for those who are into digital creativity. Please join our friends in Digital Creatives Philippines. I'm going to comment down the link for you to join them. What's more, if you're into digital creativity, inviting you to Digital Creatives Philippines. And yes, we do have a page for Onshape. Like to be updated and notified of our upcoming Onshape training. We are in Facebook. It's Onshape users worldwide. Okay, and of course, we are an advocate of LinkedIn. Onshape users worldwide is also in LinkedIn. So, of course, if we have a page, we also have a group. So, commenting down the link to our group. Hoping to see you here. And lastly, if you're into architecture, engineering, and construction, inviting you to join us in BIM Philippines. And lastly, for you to be updated, notified, and reminded of our upcoming Onshape trainings, please do subscribe to us in Onshape users worldwide in YouTube. So if you're there, head over to videos tab under uploads. Simply select upcoming live stream. So what I'm seeing now is our lineup of upcoming trainings with Onshape. So sheet metal coming this June, July, August 20. Okay. So once more, it's Onshape users so worldwide. Of course, we also would like to thank our friends in Benildian Industrial Designers. Yes, we do. We also have an audience. Good evening to our industrial design friends. Okay, from the College of St. Benilde to Bicol University College of Engineering Student Council. Thank you for making this live stream possible. To our friends in Bataan Peninsula State University, to Palawan State University, to College of Engineering Student Council, UEP Maine, CPSU, JPSME, to our friends in Iris as well, to our friends in TUP Taguig, JPSME, CMU, and to our friends in Don Mariano or DMMMSU, JPSME. Okay, so let's get to know our sharer this evening. Okay, so our guest sharer is a graduate of Georgia Institute of Technology with a degree in aerospace, aeronautical, and astronautical engineering. He also has his master's degree in GIT or Georgia Institute of Technology. Please say hi and good evening to Bob Tipton. Good evening, Bob.
Good evening. How are you this evening, Joe Mark?
Yeah. So once more, thank you so much, Bob, for allowing or responding to our invite for you to share your knowledge in Onshape, not only in Onshape but with regards to design engineering as well. So let's get to know probably Bob. Get to know him a bit further. So Can you tell us more, Bob? Why did you choose Georgia Institute of Technology on, uh, despite of other awesome engineering schools in the U.S.?
Well, at the time, ages ago, turns out my mother was a college placement advisor at another university. And we went through the various engineering association evaluations. And at the time, and actually quite frequently, Georgia Tech, as we call it, is actually America's #1 engineering school. They frequently surpass MIT, Stanford, Carnegie Mellon. And my choice was to go into aerospace because it was the broadest and most coverage of any of the programs, and they consistently were #1 in the country at the time. And over the years, they have many often been ranked as #1 in the world.
Wow.
Worldwide, they are usually ranked as the #1 aerospace engineering university on the planet. I was fortunate enough to go there and work with some of the most brilliant aircraft specialists of their time.
Yep. So yeah, I made a quick search in Wikipedia about Georgia Tech, and yeah, I can see here the undergraduate engineering program rankings, and yeah, it is for with regards to engineering. GIT or Georgia Tech is consistent always in the top three, top five rankings all around the world. So I believe Bob is also here in the Philippines. Can you share us more with regards to your journey and why are you currently here in the Pearl of the Orient Seas?
Yeah. Well, I'll keep it brief. There was a very old and somewhat violent joke when I was in school, which summarized basically that for a truly good engineer to do their job, they will put themselves out of work. Our job as engineers often is to solve problems, break new ground, discover new things, and once we've done that, they get documented, written up, and we don't really need the leading innovators as much anymore. So most of my life has been moving from difficult problem to difficult problem over the years. I spent 7 years in America's defense aerospace industry. I got to work with a man who was widely known as the best or I'd say quietly known as the best aerospace engineer of the late 20th century. He and I are still friends. But really over the years, even since high school, one of my biggest drives personally as an engineer is to solve the sustainable energy crisis. And at various times I've focused on and off that since 1976. And about
Wow.
2 years ago, some new technology became available, primarily in the battery arena and in underwater robotics, and it broke the logjam for me. So I started putting most of my efforts into ocean sustainable energy concepts and designs. And soon, hopefully within 2 months, a friend in America will have an online interactive page showing the ocean energy density around the world. And I expect it will show that the Philippines is sitting on the sustainable energy Saudi Arabian oil fields in your oceans.
Wow.
We did one back of the envelope calculation during that discussion. And if you take the area of the Tongon Strait between Negros and Cebu and multiply it by the average tidal height and assume it happens up and down one cycle twice a day, up, down, four half cycles, about 16 billion cubic meters of water move up and down in that strait every cycle. And for all 4 cycles, that's about 64 billion cubic meters of water. The entire Amazon rainforest only moves 20 billion cubic meters of water. So the Tongon Strait alone is about 4 times as much energy moving in the water as the entire Amazon rainforest and all the rivers combined. And we have the Bohol Sea, the Gulf of Cebu, the Sulu Sea, and our neighbors in Indonesia, Malaysia, and out to Papua New Guinea, all the way up to Thailand. If I am successful in making this technology prove out, we in the Philippines will be the leaders in sitting on the biggest source of cheap, sustainable energy on the planet. That's why I'm here.
Wow.
But I have to prove it. that ultimately is an engineer's job, is to change all this wonderful talk into actual proof.
Okay. So, what do you have in store for us this evening, Bob? So I'm currently sharing now your screen, so everyone is seeing your screen now.
All right. I will begin the presentation. Feel free to ask questions and step in as we go along. One of the more interesting, challenging, and rare skills I picked up over the years was surfacing, CAD surfacing. When most of us think about mechanical design, we think about something like this first image I have up. Just confirm that you're seeing a disc brake assembly, Joe Mark.
Yes.
Okay. And most of us think about mechanical design and so forth in terms of metal parts, things of this sort. I gather we have some industrial designers listening this evening, and the work they do is directly similar to the stuff I'll be covering this evening. But on the rarest form of mechanical engineering and design are shapes like this one, a fairly recent Lamborghini. And there's a huge amount of mathematics, engineering, and design skill that goes into laying out the lines, as we say in the business. And I don't want to discourage anyone, but it also requires a great deal of artistic talent. And over the years, I have found that it's a very rare person who can bring together the artistic skills, the mathematics, the CAD skills, and the engineering skills to produce a shape like this, which is probably why I think these are usually running around 2 million euros a piece. And a large part of that is due to their attractive appearance. So that's an automotive example. I've never worked in the auto industry. My area has been more in the aeronautical side of things. This is a modern America's Cup hull, a very complex surfacing problem in all respects. You have the hull itself. You have the reflexed winglet hydroplanes. You have the armature and so forth for deploying the hydroplanes. It's you look at this, and I'm actually astounded. This is one of the most beautiful pieces I've seen recently. But you also notice there's some ripple and odd distortions appearing in the image here. It's very hard to tell if that's reflection from the landscape or if there's actually some defects in the surfacing. So what we're talking about tonight is how our listeners, those who are interested in mastering or learning these skills, the techniques for how to produce shapes like this. And they all go back to a fundamental skill called lofting. And this is a very old drawing, or a replica, reproduction of an old drawing of how we have built ships pretty much around the world for 1,000 years or more. And each step along the way, we take sections, and each section is we call it a family of curves, where each curve at each location is very closely related to its neighbors, so you arrive at a smooth result. And back, 500 years ago, Magellan's time, this was done by hand with pen and ink or pencils. They would use a thing called a spline, which was actually a physical piece of soft wood with lead weights to hold it in place. So they would very carefully move that wooden spline and the weights to produce a shape, and then take a pen or pencil and trace the shape on parchment. And they would do it at full scale. So a full-size ship would be done in actual boatyard loft. In the upper rafters, up in the loft, in the attic, so to speak, they would lay this out. And my design professor told me years ago that in many cases, the people doing this would be hanging on trapezes. They would be hanging by ropes. And they would have people who would like move the ropes over to a different part of the drawing. This was not an easy task at the time. Nowadays, we do it electronically through CAD systems. Now, this is a system I did do some consulting on years ago, a very tiny amount. I was brought in to consult on some internal materials work here in the nose. The work I was doing was on other projects, which I unfortunately am not allowed to show photos of even 30 years later. But this is the YF-23 competitor to what is now the F-22, and widely regarded as one of the most elegant surface lofting pieces in the aircraft industry. These were nicknamed Black Widow and Gray Ghost. And this was actually a faster aircraft than the F-22, primarily because it's smoother. One of the roles of good surface modeling is to make a shape that is very, very efficient fluid dynamically. And we'll be spending a lot of time discussing that this evening. So for the same size engine, the same weight aircraft, this vehicle was maybe 5 to 15% faster in most situations than the F-22. And it was much harder to see on radar for similar reasons. The time they spent lofting it, they came very close to perfection, and it was just an extremely good piece of work. Until you view it from a different angle. And this is an example of how even a excellent loft may still have some defects. And it's debatable whether it's truly a defect or intent. But you'll notice that down here in this region, this really is a trapezoidal box, which they have filleted. And the same back in here. The cockpit region, they've done a much smoother, blending operation. But ever since I first saw this, I wondered, why was this not a full arch and this not a full arch? Obviously, the engines are cylinders, and the same here. And it would have actually been more effective. And I never got to talk to the designers, but the assumption is that it was just too time-consuming and expensive. For the computer power of the day and the amount of time involved, it's extremely laborious to redo these surfaces. So frequently, you allow extra room or take some shortcuts. Nonetheless, this is still one of the prettiest aircraft lofts you're likely to see. Here's a simpler one, which we'll be discussing in Onshape. After you're doing a lot of Onshape refreshes here, bear with me. And we're going to be building up into doing a similar problem to this during the discussion tonight. This is a 1/2 hull of a hypothetical sailplane model. This one, as the label says, was done at half scale. And it's done through one Onshape procedure, a feature written in FeatureScript. And this entire loft was done in 18 features, including a couple of transforms at the end. And actually, I'm underselling that because along with the loft is the entire mold support structure and back frame. There actually is one procedure, one feature added to Onshape, which is responsible for making the entire mold frame. And this particular mold frame was intended to use a high-end 3D printer to produce the mold back structure, and a different 3D printer to create the mold face. And the goal was to be able to loft, fabricate the tooling, and produce an aircraft hull in under 30 days from start to completion. And that work is still under research. Skipping ahead somewhat, we have a feature which you won't find in your version of Onshape, called lofted hull. And over here, we have a FeatureScript file. And in that FeatureScript file, there is a feature called lofted hull. And this document is available for sharing online as part of the course. And I'm not going to go through the details of this at the moment. This is a little bit of a teaser for later in the session. But basically, what FeatureScript allows you to do is write your own features and add them to Onshape. And we'll come back to that a bit more later. So basically, everything in this image you see here, from the loft and the function itself, queue up here, we can change the number. Actually, this is coming out of a parameter. But we can go in and change the number of sections on the loft. We can choose to mirror it if we want. Pick up the other side automatically. We can change how the sections are distributed. And we can change the tightness of the curves. So if we make the curve at full strength, we get a very square shape. If we make it at half strength, we get a more rounded shape. We can make all those adjustments. And it's based off of 3 splines. There's a outer edge spline, which projects down to become the side. And there are 2 top and bottom keel splines. And from those 3 curves and a bunch of code, we produce a lofted shape. Moving on, as I said, the surfacing and shaping, all CAD models are effectively surfaces. You'll hear them called solids and so forth, which they are. But a solid is simply a surface which encloses a volume, and internally in the code, the volume has a little checkbox ticked off that says this volume is solid. If you clear that checkbox, all of your solids will become hollow surfaces. So really, surfacing and solids are very similar. This shape is one that came out of my research over the last couple of years. And by properly controlling the shape, I'm able to generate a very intense vortex off of a sail-like structure. And analysis shows that this structure is actually taking energy out of a moving fluid at mechanical efficiencies that are comparable to a well-designed turbine, something that was frequently regarded as not possible. But for tonight's discussion, all of this has to do with proper shaping of the surfaces. And this entire model was built in Onshape using FeatureScript. And one of its predecessors, and this shows what how proper shaping and surfacing can really have a huge impact on design. On the left, we have a hemisphere, a hollow hemisphere. Basically, this is a fairly traditional approximation of a parachute. And over here, we have the same area, frontal area, split between 2 sail-type structures, which have been very carefully surfaced and aligned. And you'll notice that in the trailing wake of this shape, we have completely stagnant flow. There are no streamlines circulating here. Basically, all the air or water dragging behind this thing is quite literally stagnant. It produces really no force, very minimal force on the device. Most of the force is coming from the high pressure inside. But if we shape it properly with good surfacing, we can stir that flow and produce very powerful vortices. And these darker blue areas are areas of low pressure, equal to almost half the frontal pressure, negative in the back. So we've increased the drag on this device by as much as 50% by proper shaping. And that's really what the work I've been doing on this job most recently has been. This is a similar, more evolved shape viewed from the front. And it's just a cool picture. And most of what we're discussing here are the CAD techniques for designing shapes like this. I'm not going to turn this into a computational fluid dynamics lecture.
Bob?
Yes.
They have a question. What software was used to model that CFD?
The model or the analysis?
Yeah, the analysis. So what software was used to
OpenFOAM.
generate that? Okay.
The geometry was all generated in Onshape and FeatureScript, and the analyses were all performed in OpenFOAM. I hope to get some money together and do it in Fluent or Exa, something with a much better meshing tool than OpenFOAM provides. The real barrier there was in the meshing. So this is, again, open this up. So this is a feature I wrote, Sail Loft 3. And it's similar to the aircraft loft, except in this case, it only required 2 edges, here and here. It has the same sort of control parameters, and it allows you, or allowed me, to make variations on these shapes very rapidly. Moving ahead. I should have refreshed all of these while we were waiting. My apologies. A compound version. And in this case, one of the design challenges, so I'm going to hide this. Actually, I'll hide this part. One of the design challenges was to produce a sharp termination off this surface, so that it made it easier on the CFD package if we did not have a blunt trailing lip on this edge. In the real world, it makes very little difference, but in the CFD meshing tool, having a true sharp edge here simplified the problem immensely. So this actually has its own feature, which is an edge loft feature. And what this feature does, if we zoom in carefully, is it takes this edge, and this outer edge, and it has one starting vertex just to help me decide where to begin. And what it does is it produces two tangential surfaces from this face to this edge and from this face to that edge, thus putting a curved knife onto the shape. And again, that's all done in, make sure I get over here. Here's the sail. I'll close off that portion. I believe somewhere, I think I have lots of versions of the lofting here. Oh, I'm in the wrong tab. So there's a special edge loft feature, which allows you to do this. And, it's code. The FeatureScript looks a lot like, it's based loosely on JavaScript. So if you've done some JavaScript programming and are good at CAD, you can usually pick up FeatureScript fairly quickly. And then moving on, we'll go through this one quickly. Well, once it's loaded, I will move through it quickly. And this one's making use of both an edge sharpening feature, and it's also making use of a rounding edge feature, so that we don't get fluid detachment on this edge. We need to have a fairly fat edge to keep the fluid from detaching in here. And that's also another feature written in FeatureScript. So the basic loft is in FeatureScript. The edge, and this allows us, even with 71 features, it's a very complex piece. As I said before, all lofting really goes back hundreds of years to the same basic concepts. We start off usually with a 2D sketch, Let me move on to this. So it's perpendicular. We basically have sketch curves, dimensioned. I find that one of the fastest ways to get from a 2D sketch to a 3D sketch is by surface extrusion. So we're making use of Onshape's surface extrusion feature. You enter to begin it, you would enter the extrude tool, and then you have a choice between solid or surface. So in this case, I chose the surface. I selected this edge, and I arbitrarily extruded out 30 inches. I did the same with one of its neighbors. So I have these two curves. I created a second sketch, which is in this case, it's a bottom view, which is going to be the gunnel and shoulder curves. They're very specific terminology for many of these curves in the nautical and aeronautical industry. These are usually called keel curves or spine curves. There's also a shoulder curve and a chine curve, a gunnel curve, or maximum waterline curve. We then extrude that surface to here, and we've limited that one. Wait a minute. Edit the extrusion. So in this case, I've told it to extrude this curve up to this face, and that's limited the extrusion to that position or to that boundary. And if we hide this surface, that has produced a smooth compound 3D curve. This 3D curve is now the intersection of the extruded surface here along with the extruded surface here, and that's going to become the gunnel line for this particular loft. We then continue the process. We have another surface coming down here, and these get rather busy. You end up doing a lot of hiding and removing to see them. But if we hide this, hang on, I just want to hide this one. We have this is going to become what's called the shoulder curve of the loft here. That's going to be the loft shoulder curve. And we now execute a hull loft on this. What happens in here, what's done, if you do this by hand, you would have to go in and create a plane. In this case, we use a 3-point plane from this point to this point to this point, and then make a sketch, and then put a spline through that sketch, and you would have to put a pierce constraint to that curve, and then manually adjust these tangent curves, which keep wanting to, move against each other in order to arrive at the right shape. Now I happen to know that this one and this one should be horizontally constrained. So if I do that and I make these vertically constrained, that will make this quite a bit easier. And now I just have to use these to control the tensioning on the shape. But imagine trying to go through here manually and putting one section after another along these curves just to produce the cross sections. And then when you're all done with that, you would go into Onshape's lofting tool, and you would pick each one of these curves, doing a surface loft in this case, curve, 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 all the way down to the end. That's laborious and tedious and error prone. And usually after you get it all done, you realize that you didn't have enough planes and you get to start over again. So what we're going to be discussing through this is methods of how to speed that process along. So I wrote a hull loft feature. And the hull loft feature, again, has the 3 input curves. This is almost a mantra. It's just an incantation you almost always go through for doing these sorts of vehicle lofts. Different lofting problems have different procedures that you go through here. I'm going to turn off deletion of the profiles, which I left on for this course so we can see what's going on. And what the feature has done is that same process I showed you my attempting to do by hand, poorly, is now done automatically. And I can change the number of sections. The more sections you have, the more precise you are, but also the longer it takes to compute and the slower your system will be. So usually there's kind of a search for what is a good number of sections. All right, so that's what we're going to be covering this evening. We're about the 1/3 point for this evening. So this is more or less a preface. So from here, we're kind of getting into the details of the CAD behind all this work.
Okay, guys. So if you have, for those who have comments or questions, feel free to comment down. So, okay, moving forward.
All right. So this is a more typical engineering loft example in Onshape. I have a sketch with a point, a sketch with a rounded rectangle, another sketch with a rounded rectangle, and I'm going to make use of the origin. So viewed from the perpendicular, these are just filleted rectangles, quite common. We execute the loft function, and the loft function, walk through it from the beginning, can accept a vertex. I'm doing a surface loft, so it can select a perimeter, a second perimeter, and a terminating vertex. And we can make the start profile tangent to the plane, and which you will find out as you use these surfacing and lofting tools that very frequently they fail. They fail quite a bit. So attempting to put termination conditions on this loft is actually causing it to not work. This is another reason I like using FeatureScript for lofting, because you can write the feature to overcome a lot of these problems. And then once the feature is distributed, or you have to reuse it frequently, you don't have to fight with these eccentricities of the lofting function quite as much. But imagine trying to do this for an Airbus 380. And people do it. Someone out there lofts the entire Airbus, all a couple hundred meters of it, section by section, piece by piece, following these rules to arrive at a well-formed shape. And as we've seen, that's also done for boat hulls and car bodies and industrial design components. All right. I think I have to. Okay, here we go. I'm a bit out of order. Bear with me. So let's go back and get some terminology and basic concepts down for the rest of what we're going to do. I think most of us who worked with CAD systems understand what a sketch is. A sketch is almost always a 2D construct. Let me make sure I get in the right view on this thing. Top view. Here we go. In this case, it's just a rectangle. We usually convert sketches into solids using an extrusion function. In this case, I'm using a surface extrusion. So I take the perimeter and it extrudes it up to form a brick with no top or bottom. I can make a second sketch, which is on the plane of this face, and it has two edges. And when I extrude that sketch, again, as a surface, I'm extruding these two edges. If I do them as a blind, you can see here are the edges being extruded. But in this case, I told it to go up to a face. So now the extrusions are going up to this face. And I have told Onshape to add it to, in this case, the whole model, since there's only one piece. And when I'm done, I have a solid. Well, no, I still have a surface. It looks like a solid in all exterior appearances. It looks like I've made a standard extruded brick. But if I go through and make a real solid, which looks the same, these two, they're on top of each other. So you can see they are geometrically identical. But one is marked as a part, which is equivalent to being a solid in Onshape, and one is marked as a surface. If I create a plane, splitting these, and I split one of them, splitting the part in this case, I get two new parts. And if I hide those parts, you'll see that the interior, there is an interior. Because the part was solid, when we cut it in half, like sawing a saw through a piece of wood, you're left with a new face. So when you cut a solid with a surface, you end up with a new face and the part remains a solid. If I split the surface, again, the geometry looks identical, but when I hide one of them, there's nothing inside. And inside almost every solid modeler you will work with, this is that checkbox I was referring to earlier. Going back to before the splits. This surface is a brick with an inside and an outside, but the inside has been marked void, not solid. The part is exactly the same shape, but its interior has been marked as solid. So when we split them, one produces a solid structure. Oh, do the other one. And the other produces a hollow piece. So one thing to take away from all of this is that the distinction that you'll hear through many, many computer design products between solids and surfacing really is a checkbox. At some level down inside the model, did they check off the interior, the closed off interior as solid or void? And that really, at the lowest level, is the true distinguishing feature between all solids and all surfaces. So the techniques we're going to go through for working with surfaces are the same techniques you would go through for working with solids to accomplish the same result. Most people, most of the time, will almost always work in solids. Most of our CAD systems are built to operate that way. But occasionally, surfaces provide a very useful capability. So we have a part, which is solid. And I'm going to go in and I'm going to delete a face or a set of faces to arrive at a surface. And what I've told Onshape to do is to take that solid and to delete these lower faces and to leave the body open. Don't try to re-heal it to make a new solid. So now I have an infinitely thin surface, which I can do most of the standard modeling operations on. I can fillet that surface. I can use its face of that surface to do an extrusion to make a new solid. Only in this case, I did the solid from a lower sketch and I told it to terminate at the surface. So if I exit and hide the surface, I now have a solid which exactly conforms to one side of the surface. If I do it again, I can make these legs. I can make this piece up here. And if I hide the surface and the other part, it also aligns to the other side of the surface. So when I transform these apart, I'm now using that surface to define a splitting boundary. I have found this to be a very useful technique in a lot of design cases where the boundary is well defined. You can lay that out early in the process, share the boundary, and then other models are built to align to that boundary. And we're just moving them apart a little bit more. So that's what I refer to as using a reference surface for construction. You can accomplish exactly the same result. I actually literally derived that surface from the previous part. If I edit the derived function, you'll see it's pulling in the surface from the reference surface tab. And I make a new sketch and a new extrusion. Only in this case, I overflow the surface. And if I hide the surface, you can see that's still a solid block. And then I can shell this piece. So if I hide the surface, you can see it's a hollow square tube. I can perform fillets on it, do the interior fillets. And then I can take that surface in and use it to split the part. And accomplishes almost the exact same thing as we did in the reference case, except now we're using the surface to split the two parts. And the advantage here now is that if we go back and modify that splitting surface, both parts will automatically be cut and exactly mate with each other at the splitting boundary. And we can draft the pins and so forth. And there we are pulling pieces apart. I did this exercise slightly out of order. Sorry about that. But this is basically how we produced the lofted surface earlier. So our first feature that we're going to write is, you'll notice that in order to do the loft, I needed to produce a number of planes and sketches. And if you do that manually, then you come in here and say offset plane, an inch, offset plane, another inch, et cetera, and you keep building up the planes. That can get very, very tedious. So if we know we're going to need a lot of planes, it would be handy to have our own feature to produce those planes and put them in the right positions. So I wrote a plane stack feature. And what this does is I come in, I tell how many planes I want, I pick a curve, and ta-da, I have 16 planes. Or 5 planes, or, wait for it, 50 planes. And then if that curve moves, if I go back and edit this sketch, it's underneath here. Move that down slightly. Moment. What sketch am I on? I'll just double click here. If I edit the sketch, use Onshape's final version mode, as I move these control points, all the planes will automatically update. So this is a very simple example of adding a feature. So let's go take a look at our first actual feature in FeatureScript. To create a feature, you come in and simply, as you would add a Part Studio or assembly, you create a feature studio. It's a file. It's stored in the text file. We're going to overlook or not discuss in detail this here. This is telling the Onshape which version of Onshape this feature was written in, so that if there's a later change in Onshape's programming internals, your feature will be executed exactly the way it was 15 years ago. This makes sure that changes to Onshape do not break your code later. The export call is simply so it shows up in your Part Studio. The annotation defines the name that will show up in the Part Studio. So it's called plain stack. And if we go back and look over here, plain stack 1, plain stack 2. So that name, if I go and I change that name to plain stack X and save and go back, we didn't change. That's odd. I would expect that to, maybe it's an updating issue. But if we go to create a new one, now they're called plain stack X. So we're going to go ahead and put that back. A lot of somewhat counterintuitive things happen because of Onshape's version control. I believe since we created those under the old name, it's going to try to keep the name. A feature is broken down into two fundamental parts. And I think the hardest to grasp the first time around is the precondition. The precondition is, as its name implies, it's a test that makes sure that if you call this as an ordinary function, that all of the parameters in the function exist and are of the right type. So if you passed in a floating point number for a plain count, it would reject it and say the plain count is not an integer. So this is an integrity check. It also allows you, to input queries and so forth. But the most important thing about this is that this precondition also defines the user interface. So just arbitrarily, if I wanted to put in a Boolean parameter called test check box, and we'll call it test check box. Note that this name is what the user sees, and this name is what will be used in the script. And if we save that, and we go back, and we edit this, we have a new checkbox. This is one of the least understood and most powerful aspects of FeatureScript, is that the ability to define your own parameters on the fly, save them, go back into edit it. Oh, wrong one, edit. Sorry, here we go. And we get the name updated. When they wrote Onshape, let's go back and look here a minute. We have a lot of features up here. We have extrude, so I won't go through them all, but there are a huge number of features up here. And I hear there's a sheet metal section coming up soon. I worked on the sheet metal project for a while. So we have all the sheet metal tools on here as well. If we go over to the help button and go to FeatureScript documentation, obviously all the functions and so forth are documented in here. But if you click on standard library source, and give it a minute because it's big, and we want to, oh wait, is this a new icon? Yeah, it's a new icon, didn't recognize it. You will see a whole lot of feature studios in here, a lot of them. Okay, so let's say that we or you don't like the way Onshape named some of the things in the extrude feature. So let's go down to the extrude feature, find it here. I'm going to do a select all and copy. I'm going to go back over to, try to get back to my original tab here. I'm going to create a new feature studio here. I'm going to paste that into my feature studio. Go way up here to the top. These are a bunch of enumerations, more functions. Get down here to the actual, here we go, all the documentation. And feature name transforms, not the one I'm after. Define feature. Bear with me. It's a big file. I'm looking for a particular location. And frequently you'll find there are multiple features. I'm going to do a search. Find extrude. So.
Hi, Bob. Any?
Yes. Anyway, my point. I'll move along here. This is running off schedule. The point is that given enough time and effort, you can copy the entire Onshape interface, paste it into FeatureScript, and rewrite it as you wish. I happen to choose a large one, so it's bogging down much more than I expected. But the entire, yes, get back to where we were. If you are diligent enough, you can change everything on this menu using FeatureScript. Go ahead.
We have a question. What particular programming language should a beginner should learn in order to understand the FeatureScript more?
I would start off with JavaScript.
Okay.
FeatureScript quite literally was written off of JavaScript. So I will delete this portion, but take it on faith that back here in this standard, close that tab, or this tab, every feature in FeatureScript can be found in here somewhere. And if you are patient enough and want to take the time to learn enough, you can actually change the entire interface. In concept, you can yourself, if you take the time, you can write SolidWorks UI into FeatureScript and add it onto Onshape. I would not recommend expending so much time to do that, but it's possible. So let's go back to the example we're working on here. So the plane stack, we've added a pick. We want to pick a curve, which is an edge. We have a maximum of one of them. We want a number of planes. I will delete the checkbox we're not using. And then inside the body of the function, down here, note that define feature is a function itself. The bracing is a bit odd, but this basically defines the UI, and this defines the behavior. So we run a loop on I over the number of planes. We can test if the curve is closed to determine what the t value is. A closed curve, we want to generate both 0 and 1. For an open curve, we don't actually have a closed curve. We want to generate only 0 or 1. For an open curve, we need 0 and 1. We evaluate the curve. So evaluate, some of the function names are not too obvious, but to evaluate an edge, we evaluate a line tangent on the edge. So here's the edge input, which is the base curve that we picked. And we evaluate it at t, computed by the plane count. We get the normal for the plane off the line direction. We get the origin for the plane off the line origin. And we tell Onshape to do a plane operation on the origin and the normal. And we get back of planes. I had planned to take a break at this point. I think that's a pretty big bite. We're going to continue in a few minutes, but if anyone wants to get a drink, get up and stretch, ask any questions, this is a planned breaking point.
Okay, so I'll probably just be playing a quick video about Onshape story.
All right.
So once more, everyone, if you have comments, questions, suggestions, feel free to comment them down below. And for those who are asking about the registration form, it's open. Yes, it is. It is open. So feel free to register. So let's have a quick 2-minute break. So sharing to you Onshape story.
Before people leave for the break, quickly, just to keep people's interest, one of Onshape's challenges has been that there should be a huge market for custom scripts, but we have yet to find people willing to write them and ways to market them yet. So I believe, and we have believed for a long time, that if we can find a way to write and market these on demand, there is a small industry out there ready to start. So as you take your break, think about that. I'm going to take my break also.
Okay. 3 minutes, 5 minutes.
It used to be that you would design under one roof and then manufacture under one roof. What we've seen is a lot more specialization. Expertise has become fragmented, and as a result, each of these people need to coordinate and work together in the design process. They can be across the state, across the country, across the globe. And so people need tools to be able to interact and communicate. We took the opportunity to look at how the CAD world had evolved, how product design had evolved, and how the computing infrastructure had evolved. And we decided to hit the reset button on product design software.
Onshape is building a new generation of CAD, one that's designed for teams to use. Everyone on the team can use it anywhere, on any device, anytime.
We're capitalizing on the platform, the cloud, mobility, and redesigning essentially what CAD is to help people design products faster, easier, and more affordable.
20 years ago, when we built SolidWorks, we built CAD on the modern computing platform, the Windows PC. It runs only on that computer. When it comes time to work as a team, users have to use all these schemes to copy files, check in, check out. It's kind of a hassle and it costs them time. Today, CAD still runs on that Windows PC, but people are used to using their phone, their tablet. People are used to working on multiple computers and going into a web browser.
Teams are built up and torn down quicker. There's a lot more collaboration. Tends to be a lot more contractors, a lot more consultants.
And so the rest of the computing world has changed a lot, but CAD hasn't. And it's time for CAD to evolve.
You know, users, they're like all of us. They're tired of trying to figure out what's the login password for the data vault, because I don't use it all the time. And when I get the assembly, all the links are broken.
License fees, installations, license managers.
Do I have the right version of the part or the right version of the assembly?
I visit CAD users. Years ago, I talked to them about modeling cool shapes and cool products. But in recent years, when I visit users, they're talking about all the hassles of CAD. And it's time to get rid of all that.
Users today expect that we should just be able to access information and share and work with other people real time, much like the way that Google does for working on a Word document. We've done that for the CAD world.
We get to collaborate on the same geometry, which was never done before. We have found ways to break down our modeling paradigms, our assembly, our models, our features, so that multiple engineers can collaborate on the same feature, which was never done in CAD before.
The cloud is really a transformational platform.
We put the CAD system and the CAD data in one place in the cloud, and one master copy of the CAD data that everyone can access simultaneously from anywhere through any device. So there's never any copying of a CAD system, and there's never any copying of CAD data.
When we're working on something simultaneously, you see visual cues to understand what part of the model you're working on, what part of the model I'm working on.
Even people who see Onshape once will say to me, "Hey John, can I get a copy of Onshape?" And I say, there is no copy of Onshape. I don't have to send you a copy. You can log in from any computer. You log in through any web browser and you have access to the whole system. Even if you have an iPad or a phone, you can use Onshape.
It can be used by the single user working at home, the small design professionals, small teams, through to some of the largest manufacturers in the world.
CAD users, product designers, engineers, they don't sit at their desk all day. They're in meetings, they're moving around, they're at the coffee shop, they're having lunch, they're home thinking about it on the weekends. Wherever they are, whenever inspiration strikes, they should have access to CAD, and with Onshape they do.
browser technologies, mobile technologies, and cloud technologies are converging and giving the capabilities to build complex system like ours.
What we are doing here is very forward-thinking and innovative, and we have the team that can achieve this.
We've got people who are the most experienced, talented, smartest software engineers and CAD engineers that I've met in my career.
And so it's serious CAD, it's serious design software.
You get products done faster by teams, and you'll get them done better because they have more time to spend on engineering. And finally, I think engineers and designers will have more fun. You know, Onshape's just more fun to design with.
Okay, going back. Good evening, Bob.
I have returned. Hopefully the audience has also.
Yes, they are.
Who's leading off, John Mark?
Leading off what?
Do I have any outstanding questions, or should I continue on with the next section?
None for now. So I think everyone is in awe, and but
Okay.
we have more than 80 viewers right now.
Okay. So, my hope is that in this session, I'm going to reduce your awe and show you that you can do this. Most of this is really fundamental high school, first year college math. There's very little here that is beyond most engineers or designers. It's a big bite getting into it. So I'm going to roll down to the end here to show you what we're going to be attempting to make here. And it should be familiar to most of our audience. I gather we have some possible foreigners visiting. But we have here my attempt at a fairly typical Philippine outrigger canoe. And for our visitors from other parts of the world, this hull configuration is used all over the Philippines. And I've seen them ranging from about 2.5 meters long, able to carry 1 or 2 people with a pole or a paddle, up to 40 and 50 passenger, maybe larger ferry boats and fishing boats. So this is sort of the signature ocean engineering naval architecture model for the Philippine Islands. So I am going, yes?
It's in Tagalog, it's the bangka.
Oh, thank you. The bangka.
Bangka.
Okay. Bangka.
Yep. BANCA.
Living in Cebu, I have been trying to learn Visaya. My Tagalog is way behind. So, the pieces that we're going to be working with first are the part studio for the hulls and the hull loft feature. And this one is meant to be, let's see just how long it became. It's about 250 lines. For those who are do programming, that's a small to medium programming project. It's broken up into the basic hull loft feature and its selections. And the basic loop is we orient the curves, we create the cross sections, we convert the cross sections into a form that the loft function can use. We call the loft function. And most of this piece down here is just doing some optional mirroring if you want to go from a quarter shape to the full shape. And in support of that, we have a couple of helper functions. One thing, if you've never programmed inside a CAD system, a lot of things that an operator takes for granted don't happen. For example, there is no well-behaved beginning and end of a curve. The software could have flipped them on you. So you always have to double check and do things manually. So this basically takes the 3 input edges and makes sure that the pointy end is the pointy end on all 3 curves. And if one of them is wrong, it simply flips the direction on the curve. And this section will go through and make the cross sections. We'll come back to this in a minute. So let's go back to the shape over here. So we begin with the side sketch. So we have a gunnel line in English terminology. This is the top of the hull. We have a shoulder curve here, and we have the keel curve here. Those are the 3 defining shapes for the hull. Now, one piece of advice to those who haven't done a lot of surfacing before, like I regularly see as a mistake of newcomers, is these spline curves can support a large number of points and do all sorts of crazy complicated stuff. And new people tend to want to make use of that functionality and put in way, way, way too many points. To get a really good smooth shape, each of these edges, each of these curves has 2 points, and all we do is manipulate the tangents. And the tangents are actually constrained to be horizontal on this line. And this is all to produce a smooth shape. In some cases, I will even align these tangents to be matched vertically to produce a cleaner family of curves, but whatever works for you. But I do recommend keeping your point count as low as possible to do the job. The more points you add, the more ripply the curve gets, and the messier your final result becomes. So we're going to I'm going to walk it through this way. So we're going to roll to here, and that will produce our first construction surface, which will be forming the shoulder curve. We go to the next extrusion, show that surface. That will be showing the top of the hull, the gunnel curve. We then do another sketch, which is our bottom sketch. This is the curve for the gunnel line, and this is the curve for the shoulder. Those are all created. We go ahead and do those 2 extrusions. And now we have, hiding in here, we have the keel curve, we have a shoulder curve, and we have our gunnel curve. We have another sketch coming. Oh, that was an extra one for debugging. I don't even need that one, but it's in here already. So now we go into the hull loft function, or feature. Sorry, my vocabulary is a bit sloppy. And I'm going to hide off some of these generating surfaces to try to clean up the model a bit. So the first thing we pick is the keel edge. The second thing we pick is the shoulder edge. And the last thing we pick is the gunnel edge. And we have the labels on here. I'm going to turn off the mirroring. So we go down to the fundamental curve. I'm going to hide the other surfaces. I'm going to hide this extra sketch I had in here. And now we have 1/4 of the hull. And normally these are done in quarters and halves. Very rarely will you attempt to loft both sides simultaneously. You'll just use a mirror function. Onshape has a curvature analysis feature. And what you're looking for here is if you see places where you get kinks or unusual ripples, that is a sign that your surface is not as clean as it should be. In the real world, they will actually have like a garage or room with fluorescent lights on the ceiling and walls, and people will go in here with a polished version and actually look at the fluorescent lights in the surface to see if we're getting a smooth transition everywhere. And this particular shape has a fairly sharp prow. So we get some distortion in here, but that's intended. But as you can see, that's a pretty smooth result. And that's what we're after. If I don't delete the profiles, we can see here are all the profiles that the feature is making. And I nowadays won't even consider doing this manually. Because imagine you get in here and you decide that you don't like the way you need 5 more planes. You got to, it's almost like having to start over from scratch. It's just so much work to do it over. Let's go over and look at the function. So, orienting the curves. We have this curve, and this curve are the ones we're using. We know in my use case that there will always be a common point at the beginning. So the orient curves function goes in and determines that if one of these curves is reversed, we simply set a flag to evaluate it in the opposite direction so that we know this is the 0 point for the model. So this function basically says if keel end 0 is the same as shoulder end 0, then both of these are positive. And it just goes through the logic of which pair of points and sets the flags. It's tedious, but all we're really doing is deciding, which if any of the 3 curves need to be evaluated backwards. So we orient the curves, and then we go to create the sections, which is the interesting part. So we take the number, we evaluate the base points, we evaluate a normal and a direction, we evaluate a length. We go from I to the number of sections we need. We generate a sketch ID, a unique identifier for each sketch. Onshape requires this. If you have a duplicate sketch ID, it will report an error and stop operating. We append the sketch ID to an array. Our result is simply a list of sketch IDs. And then we compute a t value. What fraction of the way along the loft are we? Which is I over the number of steps. And then we go to the trouble of we actually intersect each curve. Well, we make a plane at that point, and we intersect each curve with that plane. And that way we know that we have 3 points in each sketch that exactly match the input curves. We make a new sketch on that plane. We add 2 construction lines, which you can see here. Here's construction line 1, and here's construction line 2. We don't need those, but I added them. I'll explain why in a minute. And then we create the 4 spline points. Point 1, tangent 2, and point 2. This is an undocumented aspect of FeatureScript, which allows you to access the NURB curves. And as I mentioned earlier, when in doubt, you can actually go in and pull out not only all of the features that are used to make FeatureScript, but you can actually go in and click the Show Code option, and you will find out that this entire feature list is FeatureScript. And if you're patient and want to learn the terminology, you can actually copy paste features from this list into your FeatureScript, which is what I did here to set up the initial conditions for the splines. So fundamentally, a line segment, and a spline with an initial guess, and we solve the sketch. So in this case, we've done that about 20 times. And that's created the sections. We do have to do a little bit of projection to project points onto the plane. Actually, it's redundant, but what it does is it changes a 3 vector to a 2 vector. And also make sure it's at the right origin. The 3D intersection is in a slightly different coordinate system. So this is just a projection from 3D to 2D to get it into the sketch. So you can see here we're projecting to 2D in each one of these locations. And when we're done, we have our loft. Now, once this is up, we can change our tension factor. You can see now we have a much rounder hull. We can boost the tension factor up to 1. We get a much sharper corner. If we take it past 1, we get a reflex. And that's what these construction lines were added for. If we come in at 1.05 and come in very closely here, you'll see that the curve ran out of bounds. Very slightly, this curve went out of bounds of the boundary edge. Some people are very picky about that sort of thing. It's simply here as a visual reference. To be safe, you can keep the tension within 1. Okay. When we're wrapping up, well, no boat is actually built with all those sections in there, so let's hide those. And if you build a quarter of a boat, it will sink. So let's mirror it about the end. That gets that piece. And let's get the other half in. So we're going to mirror it about the keel. And that's done. And we use the same techniques, which I won't go through so much detail. We do an offset line to set the position of the outrigger. We do a plane and a sketch. So we're doing the same thing for the outrigger that we did for the hull. We do the same surface extrusions. Show all of those. So we're using the same exact method. And we come in here and we do a second loft. We're going to hide a bunch of surfaces in here. Hide that one. Hide that one. And hide that one. And this time you'll notice that because of the way we chose the control curves, we get a much sharper. The boats I've seen all use bamboo rods, bamboo trunks for here, but this is a more modern one with a more streamlined outrigger. And we do the same, we just repeat the same process for the upper section. Now it has a cap. So we have another same feature. It would be quite possible to write one feature that does a top and bottom cap at the same time. We're now going to go through and we're going to delete out all those extra construction surfaces. So in here, Bessie said delete all the stuff we didn't need. And at this point, we'll see that that and that are surfaces. If we do a Boolean operation on those two surfaces, we now actually have a solid part. As I said, a surface and a solid are exactly the same thing, except a solid is closed and its interior is marked as being filled, as opposed to being empty. And then just to finish it off, I did the sweep of a boom and a couple of mirrors to fill everything in. So that's basically the conclusion of the surface lofting step. So I'm going to open up for some more questions here. You may have noticed now that almost everyone, I'm going to roll back to the very, very beginning here. Everybody sees this shape and goes, wow, that is so cool. And they see the same thing for this shape and the same thing for these shapes. And then they wonder, how can I do that? Yes, Joe Mark?
Yeah, everyone is just asking that question. How can they do that?
Well, it's like how we have a joke in America, which is how do you get to Carnegie Hall, which is our great music center? And the answer is always practice, practice, practice. As I opened up with, I do not count myself as a master loftsman. I have worked with them. This takes a good intersection of artistic talent, drawing ability, style, good mathematical abilities, and a huge amount of obsessive tenacity to learn and master these things. Which is why I think worldwide there are probably only maybe 300 or 400 truly master lofts persons. It's also why Maserati and Ferrari and a few other houses have such a stable of extremely talented people that they can reliably turn out such beautiful lines. But for maritime and aeronautical purposes, the standards are much more achievable. So I always like to show this to people because every now and then there's someone in the audience who goes, wow, I got to learn how to do that. And I don't expect everybody in the audience will leap up and jump right out and do that. But the other thing I want the audience to take away is that FeatureScript, we combined surfacing and FeatureScript for this because Joe, Mark, and Elsie, who are producing this, there were two topics they wanted to cover, and I thought we could do a kind of a coverage session on both topics. The surfacing is the most obscure and difficult, but you can use FeatureScript to automate the process of building filing cabinets. You can use FeatureScript to automate the process of putting numbers on elevator buttons. Example. Actually, I opened the floor for questions. I would really love to hear some at this point. I've got about 10 more minutes to go of the material. We got about half an hour on the schedule. So I would love to hear any questions from the group.
Probably the question is, someone asked, what's the average time or how long can they learn FeatureScript? Does it take a year or probably 6 months if you put your heart into it?
I would say that you can, if you know a programming language, if you know a C-styled programming language, which is almost everything today, JavaScript, Java, C++, they're all based on C. If you have some experience, Node.js, same thing. If you have any experience with any of those languages and some experience with CAD, you can produce your first feature in an afternoon. Let me see if I can do that. If people would like to, I could probably demonstrate a from scratch feature in 5 minutes, a very simple one.
Yeah, that would be nice because we're trying to emphasize as well the importance of programming and coding, right, with our mechanical engineers, with our engineers. So hoping they that request or suggestion will be reinforced on why knowing coding is very important with regards also with CAD.
Okay, so let me see what I can do. I'm going to try to make the first steps of making a file cabinet. So I'm going to start off with a new part studio. I'm going to begin with a sketch. I'm going to make a rectangle about 28 inches deep and 14 inches wide. And I'm going to complete that out. And I'm going to make a new feature studio. And I'm going to make a new feature. Just click the button. Cabinet. I want to put in a parameter. A lot of this stuff has quick hints and so forth in the user interface. So I want to do a query, and I want this to be the base, capitalize that correctly. I want it to be a face. I want one pick. I'll call that base. And I'm going to come in and I'm going to add another parameter. And it's going to be a length parameter. I'm going to call it height. Height. I'm going to come in down here. I'm going to insert actually I want to use type completion for this. I happen to know it's called op extrude, and it has the help in here for all the entities you need. And we're just going to call it extrude. We're going to extrude this entity. We're going to, for now I'm going to be lazy, since I said I'm going to do it in 5 minutes. I'm going to cheat. I'm going to make this a vector of 0, 0, 1. Normally, I would take an extra minute or two and extract this normal from the sketch. And inbound blind, and we're going to make this value equal to definition dot height. Boom. Save it. I didn't see it. Control S is hitting the commit. I just come back in here. I now have a cabinet. Click it. I make it 36 inches high, and that's done. Not much of a cabinet. It's more of a brick. So now I'm going to add op shell. If I hit the return key. So I'm going to create the most challenging part of FeatureScript. So I want a queue for query. And I'm going to go scrolling down here. I know there is a function to do cap entity of queue created by, queue created by ID extrude. So ID extrude created a body. That's its name. I'm going to select the body. I'm going to select the cap. And I'm going to shell it at that thickness. I'm going to cross my fingers. And we have a bug. We have a problem. So I click on here. And it says, I could not find a cap entity. So since I put this on a time limit, I'm going to cheat here a little bit. Given time, I can find that entity programmatically. But here, I'm going to do it this way. I'm going to pick a face. I'm going to call it top. Oh, I'm not able to do that. I'm sorry. All right, so we're going to make use of FeatureScript has a debugger. Debug. So we want this first. Oh, I think I know what's wrong. Let's try this. So I want an end face. Still having problems. No matching entity here. So this is actually where you run into trouble. And this is where the CAD issues come in, which is we know we're looking for an end face. What other options do we have? Start or end or either. And I'd have to go back and find an example to rework here. The coding is actually very straightforward. It's the topology identification through the queries that can be time consuming. But as you can see, this is how it begins. There are other methods for finding these. And really what you make use of a great deal is this code completion to go through looking through the cap entities. So we got a cap end. Oh, I see. Here we go. Let's try this. Cap end. Let's see, cap entity created by. Copy this one and entity type face. Entity type end. I want to look at the help file here a moment. Oh. All right. Cap type. We want to reverse the order on these guys. Sometimes the auto completion makes things more complicated than without it. Q created by. Get rid of all the extra parameters. I'm going to try that one. You can see how this works. And like I say, when I do this, most of my time is spent in working out these queries. And we still don't quite have it right. So we're going to cheat. We're going to go back. We're going to roll this out to here. And we're going to extrude this by ourselves up to here. And we're going to make use of the show code feature. Oh, I need to make one more step. I'm going to do the shell here. Check. And now we're going to do the show code feature and click on shell. And there should be a query coming in here. Move this over. So we actually look at how Onshape itself did the code. So features, extrude. Should be the last feature in the queue. Sketch, 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 sketch. Those are all the sketches, right? And it should be quite visible in here because it should say shell at some point. And I'm not finding it, which is a bit odd. I see. So this is going after. Well, here's the okay. So here's extrude 1. We found it. Here's feature extrude 1. And here's feature shell 1 over here. So we'll make this a little bit bigger so we can see it. And we're after this query. So somewhere up here, right here is the query. So we are looking for, these have become very difficult to read. So this one I find somewhat impossible to read. Somewhere in here, if you decompress it, will be an English readable system for how to identify which part is being shelled. So that did not help much. But this is the challenge. Let me stop here for a moment because I said during the break, I just listened to the video from the creators of Onshape. It was something of a family reunion. I think I recognized every voice in that video. In that section. The piece that was not covered was that the intent and the hope was that FeatureScript would also be a big piece of that new CAD vision. And like many things when it evolves, it didn't quite, it has yet to evolve into what we hoped it would. But many of us still believe it's possible. If we go back and look at this for a moment, in the original days, these were not compressed. There was no compression going on here. And it would look a great deal like this. It would be something in English that you could read. And as a result, in the early days, I could just go in here and copy this and paste it into the Feature Studio, which made this step extremely, extremely straightforward. You could just boom, boom, boom. You'd be done. Make a few changes, whatever. The problem was it was too slow. The parser was too slow. So in order to speed up processing, they've gone to this compression strategy. So now working out the queries, as you learn the query language, it gets easier and easier. The longer you're away from it, which I've been away from it for a while, it can get a bit challenging. The hope was that there would be a cottage industry around the world of people, pretty much from everywhere, the Philippines, India, Central Europe, America, China, who would find markets where they could create a specialized feature and license it, sell it as code, and use it as a marketplace to expand Onshape. And that has never really come to pass. And Jean-Marc, what you were getting at a moment ago is exactly on target. Okay, you were talking about the need for CAD operators to understand programming. Was that what you were getting at?
Yep.
Yep. And this was supposed to be the ideal fit for that dual skill. And what I have been finding is that the better programmers really have very poor heads for geometry and CAD. And most of the good CAD operators have very poor heads or experience for the program. My own experience, I think I can tell you that in my 40 years, I'm the only person I have ever met as a dual operator and programmer in all of the companies I've worked for. But I have met young coming out of school who have picked up both sets of skills. It is quite doable. But the problem has been finding customers who are aware that these capabilities exist to actually create jobs to produce the work. The hope had been that the operators themselves would do this. And I think the challenge has been that even when we've found a lot of operators in America and Europe in particular who both skills. And when I talk to them about why don't you do more with FeatureScript, it's a very simple answer. My boss pays me to do CAD. My boss doesn't understand what FeatureScript can do. So he won't cut loose the 40 or 60 hours I need to write a couple of scripts and save the company 2,000 hours this year by doing that. So as a result, I'm not authorized the time to get away from my CAD assignments to actually write the scripts. And I think that has been the barrier that we have yet to really overcome. I'm told from friends inside that large companies like Daimler-Benz and General Motors and Ford, they actually do have staff on hand who are writing custom scripts inside the big company. But for most smaller operations, it's a chicken and egg problem. We need people to be able to write the scripts, and we need customers who know the scripts and are asking us to write them. So I'm also kind of hoping that someone listening out there picks up on this. I'll take some time this evening. I'll figure out the query to get that top shell figured out. There's a syntax to these things. I just have to refresh myself on doing this particular problem. And I've done demonstration. Oh, I'll go ahead and move it. So this plays into the demonstration. So we went back to our hull here. Now the industry is once you've created it, how do you manufacture it? You manufacture it this way. We have a backframe script. And let me close this so we don't have to look at it. There we go. And what this allows us to do is we can do 18-inch spacing on the panels. So we can produce panels here. We can narrow it down to 10. I have an option in here to turn off the side panels. And given enough time, this was done for a demonstration where we use a jetted ink 3D printer to produce these panels, which are glossy and shiny but very fragile. And we use a fiber reinforced nylon FDM printer, in the case I did, to produce these support panels. And we do it like an IKEA structure. So all these panels are collapsed into a stack. So we can print the entire support structure in like maybe 2 or 3 large printer runs, and then assemble the whole thing like an IKEA package. And then we take the jetted inkjet 3D printer. I keep saying inkjet because jetted 3D printers use inkjet tech. We put those panels in place, we bond them together, and we go out with a little bit of filler and some sandpaper. And I was able to produce a 1 meter example of this. Once it came off the printer, I was able to get the mold up and going in 6 hours. And we were able to get the printing done in about 24. So that's concept to female mold digitally mastered in 3 days. But it needs FeatureScript. It needs people who can write it, and so forth. So hopefully, if anybody's interested out there, we can talk about some ways you might be able to move that forward. I know Onshape had a group who was interested in trying to support this. But it's definitely a chicken and egg problem. It's definitely doable. It's quite possible. We've had college freshmen knocking out articulated robots using 3D printed parts they made using FeatureScript written features. We had a college freshman who did an entire gear train for a transmission, like 5 gears long, whatever. He wrote the gear code in FeatureScript. Once you get the basic concepts down, it gets easier and easier. And what I ran into on this problem is a topology identification problem. I know exactly which face I'm looking for. I'm looking for this upper face. The question is, how do I find and name it? And as you work with it more often and more regularly, I've been away for a year or more. That becomes much easier. So I kind of passed. I was able to write a script quickly, not quite the script I'd hoped to. And I will open the floor back to questions again.
Where is that? I have something from Kurt. Can you see his question, Bob?
Moment. Can FeatureScript be used on different CAD software such as... No, it cannot.
No.
It is the inherent... It is part of Onshape and built into Onshape, and it's actually patented, copyrighted. However, once that's done, we can export to Parasolid, ACES, Step, IGES, SolidWorks, Collada, Rhino, GLTF, STL. I think, there's ACES in there. So that gets you into AutoCAD. This one and this one get you into SolidWorks. This one gets you into UX. We can export into Rhino, so forth. So we can't actually do it in other systems, but we can export it into it and import in.
Okay. That's all the question for now.
All right. Well, get some feedback on it. I personally think that there are more mundane applications for FeatureScript, such as we had a student years ago do an entire car frame, all the abutments and infittings for a pipe structure car frame and FeatureScript, and about 20 features. So once you get the idea, the query language is probably about a 1 week to 2 week learning curve, and you're constantly hitting queries you haven't run across before. The basic concepts are very easy. So that's it.
Okay, so uh, can we bring in over Miss Nelsie for announcements and what we can expect next meeting? I believe this is a two-part series. Uh, Once more, can we confirm, Miss Nelsie, if this is a two-part series or?
Sir Bob? Well, I hope it's our series for tonight. It ends tonight.
That was my understanding as well.
Okay, so what can we expect next meeting, and when is that next meeting?
Well, next meeting we'll be having a different topic. It's let me check what's our topic for next week. So while I'm checking, no, Sir Bob, do we have an output for them? What are they going to do? What's their homework?
I'm
Do you
having
require them to
trouble
have homework?
hearing you. Let me turn my volume up.
We're seeing your slide, Bob.
Yeah, I think Nelsie was
Okay.
asking about what we were expecting the class to work on. So I basically it's a long section, but I had one or two basic one set of tasks in surfacing and one in FeatureScript. Let me see if I can bring this one back up. These are all shared publicly.
Any resources for them to start out learning FeatureScript?
All the stuff I've done shown tonight is available publicly on Onshape. You can make copies of it and read it. So that's the biggest resource. First assignment, going back to here, was to, using this model, split the flange with a parting surface. So here's the flange, and we want it to end up looking like this, using one parting surface to split the part to do that. That's a basic CAD operation without FeatureScript. And then take the example from back in this section. Basically extend this example into something more like a rocket-shaped rounded square section. Basically, as an assignment, take this piece and make it look less like a Turkish minaret and more like a rocket. And again, that example is available online. And then on the FeatureScript side, I had an interesting one, which is there are a couple of small errors in the outrigger boat example. I left them there intentionally. And usually the best way to learn programming is to take an example that works and work with it. And then once you get that down, start expanding. So my intention was to let students take the example that's there, come back to me and see who can come up with the most number of defects in the way the thing was made, both design-wise and coding-wise. And then if you go back and look at the image, go back and look here. if you go out and actually look at a real boat in the real world, let me bring this back up. You will see that the hull adheres to this corner much more tightly than it does in my case. It usually fills this corner a lot more closely. So I was going to give an assignment, if someone wants to play with it, try to modify the lofting code to see if they can find a way to tighten that up. And anything's fair game. You can write your own functions. You can play with the ones I have. You can split up multiple curves. I have always found that the best way to enter into this sort of thing to take something that's already working and expand upon it. Trying to start something from scratch is, unless you're in a formal course where we get to see you 2 or 3 times a week and offer assistance and go through, over a 8-week, 12-week period, how to do each step along the way. The fastest way to dive in is to take something that works and change it. And Onshape has a versioning system, so if you make a copy and then you lock in a working version, you can always go back to where you were before if you make a really bad mistake. So those are the just to recap. So those were the assignments I had envisioned. And of course, if someone wants to substitute one by take on the task of using FeatureScript to do some other operation, that's fair game as well. I want to recap. This was a very open briefing, and it was combining 2 very difficult concepts. If anybody's interested, if anyone requests, we can go back and begin with a much more straightforward example, like a file cabinet or a letters on a button or something of that sort. That's much easier to enter on. This was really the intention of this presentation, was to show the audience just what we can do if you choose to. It was intended to be a very, both to impress, hopefully not to scare people away too much, but hopefully to inspire someone to realize, well, if it's everybody's doing it, this doesn't look so easy. So maybe if I can learn to do it, I can do something, more interesting. So it's a challenge.
Yeah. Okay, so I hope everyone I hope this is an eye opener, most especially to the young ones who are enthusiastic about CAD. So once more, if you're interested, as Bob mentioned, if you're interested in learning more about FeatureScript, he's highly suggesting you start off with JavaScript. Okay.
Yeah, you definitely, for the programming language, if you have JavaScript, are fairly comfortable with it, the coding aspect of FeatureScript will be straightforward. The CAD topology identification is always the challenging part.
Any career advice for the young ones, Bob, or for those interested who take the path or journey similar as yours?
I have a huge amount of it. We're kind of running over time. My most general advice is that if you choose to go down the most challenging, difficult routes, you run the risk of also finding lower demand for employment. I think that's probably been the most challenging thing in my career. There have been times where I have been told I'm one of the top 5 in the world at some of the stuff I do, and I feel fairly secure. And then 3 years later, market demand for what I do has gone away, and suddenly I am now the best marble sculptor of Venetian statuary in 21st century video game playing America. As in, I have a bunch of skills that are no longer of great value. But on the other hand, if you happen to hit the market correctly and become a lead loftsman at Ferrari or Lamborghini, you can be set for life. So it's a challenge. It's a difficult challenge. I personally advise most young people to focus on fundamentals and problem solving, and not to focus on rote copying and formula work. The formulas do change over time, and you can find yourself lost. That's enough, I think.
Okay. Thank you for that. Miss Elsie, any more announcement?
Okay, hi everyone. We'll be waiting for your output. We'll be posting something in our group on how you will submit your output. Okay, and to those who want to watch the replay, it's available in Onshape Users Worldwide YouTube channel. You can review the video so that you'll be able to do and submit an output. Okay, and we'll see you. We'll be having a separate topic for next month. Stay tuned. What will be the topic? But our fourth CAD series will be on August for sheet metal creation in Onshape. Okay.
We don't have anything for July?
Yes, we don't have a CAD series for July. So it's we'll be having a different session. Just stay tuned. And we'll be releasing all the certificates for the series 1, 2, 3 to those who wasn't able to receive their certificate.
Okay, so once more, it's been an honor and a pleasure hearing from you, Bob, and sharing your expertise to all Filipinos, not only Filipinos, to all Onshape enthusiasts worldwide. Once more, thank you so much, Bob. And yeah, we hope to see you again. I guess
Well-
this is just the beginning.
Yeah, my hope was to find a few people who were inspired by this. This is definitely not something for everyone. So I hope someone out there found this thought-provoking.
Okay, so yep, feel free to connect with Bob in LinkedIn. I guess his name there is Bob Tipton. If you have more questions or suggestions.
All right.
Okay, so once more, thank you everyone. We hope we have been a blessing to you all. So yep, yeah, hoping to see you next month, next week. So once more, if you have questions, feel free to message us in Onshape Users group worldwide in Facebook or in YouTube. So Bob, thank you.
Thank you for having me.
And hoping to see
Salamat.
you soon. Yep. Maraming salamat po at magandang gabi sa lahat. Maayong gabi sa inyong tanan.
Ang gabi.
Onshape is the only product design platform built from scratch using the latest cloud, web and mobile technologies to complement the way today's professional design teams really work. With Onshape's unique database architecture, you can build complex parametric parts, assemblies and production-ready drawings together as a team. Unlike old CAD, data management is built in, so there's no waiting for files to be checked in or checked out, no accidental overwrites, and no expensive PDM software. You can explore new concepts, new ideas and new design scenarios simultaneously within the same document, merge changes together, and browse every design change ever made, so your entire team can design with confidence. Sharing design data with your team, your suppliers, and even your customers is easy. Simply enter their email address, assign access rights, and click Share. Clicking the link in the email opens your document in a browser or the Onshape mobile app for instant editing or viewing. Sending CAD files in unsecure email attachments is now a thing of the past. For the first time in the history of CAD, teams can work together on the same assembly, same part, even the same sketch for true real-time collaboration. As team members edit or create new features, updates are reflected everywhere, within seconds, so the entire team can see the impact of a design change instantly. With simultaneous access to the same CAD data, design workloads can be shared easily. Every team member, partner, or supplier can contribute in real time with no restrictions, enabling projects to be completed in record time while maintaining full control over your company's intellectual property. Whether your team is located in the same office or across several time zones, Onshape's powerful collaboration tools inspire teamwork and boost your productivity. Teams work better in Onshape.
Okay, so once more, thank you so much for those who joined us this evening. Okay, and see you next time once more for our next series of Onshape trainings. Good evening and God bless everyone. Stay safe.